Great. I think I'm happy to begin now. Well, hello and good afternoon, everyone. Hope you guys are all doing well and doing good. Um, Today, we're going to start discussing digital evidences and understanding the various types of technologies we can come across as forensic investigators and being able to understand the implications of those different types of technologies or those different types of storage mediums. I think it's very, very important for us to really understand that because that gives us better awareness of the sort of tools that we could potentially use to help us analyze the data that we're looking into. Okay. I'm getting some feedback noise. That's yeah, that's part of my challenge with Teams. Um, so yeah, please, if we could all make sure that you guys have muted your mics, that would be really good and helpful. So at least we can have a hassle-free session. Um, so yeah, going forward, I think we're going to try and stick to Teams for the time being. I know the general guideline from the university is to use Engagely, but that has not really been effective. So for example, a lot of students complained about being kicked out of the session last week. So I think going forward, we'd stick with Teams and see how things go for the next couple of weeks and keep it moving from there. Okay. There'll be some general information around coursework. I'm happy to do that tomorrow, so I'll give you a bit more guidance and information around the digital evidence that you guys are going to be using for your investigations and the processes that you need to follow to be able to approach Fireware to have access to those. So yeah, I'll give more information around that next week. Okay. In terms of what we're going to look at today, so I mentioned earlier, really sort of looking at the different types of technologies or storage mediums that we can encounter, understanding the differences between these types of storage mediums and the potential implications for digital forensic expert. The next thing that we're going to be discussing is data imaging. So we're sort of familiar with data imaging. We've been able to utilize FTK Image as a software to help us with that procedure. But again, it's also important for us to really sort of understand the various methods or other approaches that we can use for imaging as well. So it's not just software imaging, we have other procedures that we can use. Image format, very important. So I did mention to some students last week that it's quite open for students to decide what sort of format they want to create their data images in, but I would love to see some level of justification within the coursework report. So we're going to look at different types of image formats today, and of course, highlight some of the advantages and disadvantages between those different formats as well. And then finally, have a general discussion about the types of imaging software that we could utilize. Okay, so we're quite familiar with this procedure. We know that there are two scenarios that we encounter as digital forensic experts, one of them being static acquisition. And essentially, that is quite easy for us because we know that the machine is powered off. All we have to do is essentially open the PC tower and extract the storage mediums that we're interested in. And this is also quite a suitable approach because it allows us to comply with all of those different principles and guidelines that we've sort of discussed on the whim in the past. So for example, ACPO Principle 1 states that we as the forensic analyst should always ensure that we do not carry out any action that could potentially tamper the data stored in the hard drive itself. So the process is actually very repeatable and easy and straightforward. But it's not generally considered the standard approach for a number of reasons. So for example, digital forensic experts are now starting to get interested in understanding and having access to live data because we really want to have a general idea about what are the existing or live processes that have been run on that system so we can have an information or general idea about the main intention or the goal of that particular person that we're interested in. This is more relatable to things like incident response, where somebody could be utilizing specific type of software or tools to carry out some form of cyber attack. If those tools are actually running live on that machine, we would like to collect and gather as much data about those different tools and the processes that are executed by those different tools. So that essentially makes the requirement for having access to live data. Network connections, very important, so we can have general idea and information about some of the network actions or connectivities that this person has been engaging with. This will also give us a bit more information about the actual nature of the incident that we're investigating, but also the intention of that particular person and some of the other external factors that could be associated to that incident as well. Okay. But the challenge with that is, unlike other forms of data where we could essentially use those metadata that comes with the files, RAM data does not have any metadata associated with it. So for example, things like date and timestamps are not available to any of the information that we're going to come across. And that makes it very, very difficult to establish things like timelines and really getting a general idea of the time frame it's taking for activities or incidents to take place. But nevertheless, it's still relevant, it's still important. And even if in the process of the acquisition part itself, we're going to have to interact with that machine, we're going to have to interact with that system, we can rely back on Akpo principle number 2, which states that we are able to make some changes on the system as long as we minimize those changes, number 1. Number 2, we have to make sure that we're competent enough to do so. And number 3, we have to be able to explain and justify our actions, which is why I keep emphasizing on that third point, really. You know, the evidence images that we provide for you are there, they're open. It's up to you to decide which approaches you want to take to analyze them. But that element of justification is very, very important. Because one of the things that you have to remember is that if you're presenting that evidence in court, there'll be an expectation for you to be able to explain those actions. And the people who are going to be receiving that information might not necessarily be people who have sufficient technical skills or technical background. And that element of explanation and justification is very, very crucial. So please make sure you take note of that. Okay. So the common terms that we tend to use around the process of extraction itself or making data image is imaging. So you might have heard me say this term quite regularly. And essentially what we're doing by imaging is creating a replica or an exact copy of the data itself. So the data as it is without any differences. But there are other terminologies that you may come across within the literature. So some of them being things like bitstream copy or bitstream image, mirroring or sector copy. All of these terms essentially mean the same thing, okay? Now, it's also important for you to know that imaging and data copying or data backup are not the same thing, but I would explore those in a bit later, okay? So the imaging process, very, very essential, very, very crucial. We always have to ensure that we create 2 separate images. So we have our existing data artifact, or the destination source, the source of the evidence. When we apply any form of tool that we want to create the image, we should always ensure that we create 2 copies of that particular image. Now it's up to you again to decide whether you want those 2 images to be in the same imaging format or whether you want them to be in separate imaging formats. The justification that you provide is going to be completely up to you, okay? The standard procedure with what you would usually find in industry is the backup copy is usually sort of the DD file or the raw format file. So that becomes the control copy, which we use for any backups of we need to exchange that data or information with any external third parties. Whereas the one that we use for the analysis and investigation could be either an E01 or AFF, depending on the type of tools that we as an organization are more conversant with, okay? So again, those are choices you have to make at some point. But again, please do remember that that justification is very, very crucial. All right. Now, what we've been doing is looking at data or looking at a USB device and creating an image out of that USB device. So that essentially means replicating that data into a single file, which allows us to be able to use tools like FTK Imager to analyze that information. But we also have hardware imaging, where we have 2 forms of hardwares. One of the hardwares containing the evidence, and we essentially replicate that copying process or that data extraction process and transfer that information into the destination drive. So again, something for you to be aware of that in some instances, particularly when you're dealing with very, very critical cases where there's a need for you to actually perform the imaging process within the crime scene itself, it's always important for you to ensure that you have sufficient access to various types of storage mediums in case you need to conduct that physical imaging procedure, right? Now, a very, very important criteria is verifying the hashes of the files. This is very, very important because again, we have to ensure we maintain data integrity. we have to demonstrate that there are no changes throughout that data acquisition process. So one of the main approaches that we tend to use to demonstrate that is utilizing things like hashing algorithms. So hashing algorithms allow us to take an input file or a set of data and utilize a hashing function to be able to transform all of that data into a fixed string size. That fixed string size is what we use to demonstrate that there have been no changes from the actual source that contains the original evidence and the destination of that particular image. FTK is quite useful because it's able to do that for us utilizing two different hashing algorithms, so both MD5 and SHA-1. We do know that these algorithms within the context of cybersecurity have their own limitations, but those are mostly generally for security purposes when we're dealing with things like storage of data passwords, etc. So because they're quite susceptible to things like collision attacks, etc. But for the purpose of hashing, we tend to find that these two algorithms are usually fine and are capable of doing the job. So again, make sure this part of the acquisition process is always documented, is always provided and emphasized within the report itself. Okay. Good. So part of the challenge with data backups is the fact that we don't have access to all of the data or all of the files. I was having this discussion with Scott last week, I believe, and we're looking at that USB devices. And one of the things that we're examining within that USB devices is things like the Slack files, for example. So with the Slack files, even though the file has already been deleted, we could utilize that Slack file to be able to get some generic information about the original name of the file that existed within that particular storage space. We could also get things like date and timestamps associated to that original file as well. So sometimes that could also be helpful for you when you're trying to build a case or identify various potential sources of evidence. So yeah, when we do a data backup, data like Slack spaces, data like swap spaces, deleted files, unallocated sections, all of those data do not get copied across when we do a data backup. And that's part of the challenge that we face as forensic experts with the data backup process. It's generally not considered an ideal procedure for making a data image, okay? But in some cases, so in some instances, that might be the only option that you have. So for example, if you're dealing with a machine that has access to data that is stored remotely somewhere, then obviously we cannot make an image of that data because that data or information is stored in a remote location. All we can do in that instance is copy the available data that we have to us. So again, something for us to be aware of, right? Generally, what you would find is if, say, for example, you have a hard disk drive with, say, 800 gig of data, 800 gig of storage, that 800 gig of storage contains, say, 200 gig of data. If you were to make a backup of the files contained in that particular hard drive, what you would get is 200 gig of data because the file system is only going to recognize those different partitions that contain relevant data or relevant information that it can recognize, okay? Whereas if you have the same data storage medium that has 800 gig of data, if we do an image or bit stream of that particular device, what we get is an outcome or a destination source that has the same size of storage medium or storage capacity, depending on the imaging format that we're utilizing. So again, here we can see that all of those additional information, like the swap spaces, the Slack spaces, the deleted files, all of those are going to get copied across. Okay. Good. So now the next thing that I really want us to explore is look at the various types of storage technologies that we can come across. So two of the most common technologies when it comes to storage mediums are hard disk drives and solid state drives. Okay. I have one of the very, very useful video that I want us to watch and a set of questions that I'm going to ask you guys later. So I really want your participation in this. So I would really recommend and encourage that you pay attention to the information that is going to be illustrated in this particular video. Just before I proceed, are you all okay with having, can you all hear feedback from the video? All right. Thank you, Joe. Appreciate that. Thank you. Great. So moving on, are we able to identify any of the components highlighted in the diagram that we can see there? Any ideas? All right. Sector A, the head, not really. I think, yeah. So A is not the head. So I have a hard disk here with me. You can essentially see some of those same components that are being discussed there. We can certainly see in this instance that we have two platters, right? Each platter has two surfaces. That essentially means that data can be written both on top and on the bottom bit of the platter itself. This is the component that we refer to as A here that Scott is saying. Yeah, that's fine, Scott. So this is the actuator arm, right? So the actuator arm is responsible for moving all of the read and write heads that Scott mentioned earlier for reading data or writing data across the actual disk itself. Okay, quite a very, very useful and handy component. So we know A, we know B, we already know C because I mentioned that already. So C could, depending on how we interpret the image, C could be the actual platter itself, or it could just represent one surface of a platter. All right. D, I think someone mentioned that D is a track. So that's a collection of data stored across the whole entire sphere of the track itself, I mean, across the whole entire sphere of the surface. E and F are pretty much the same thing. So E and F are the sectors. Those are the smallest units of sizes. So one of the things that we tend to see when we go into FTK Imager is that it can tell us the exact sector where that particular piece of data is stored in. G is also a very important component. So that's the spindle that's responsible for rotating the actual drive itself or the platter. So that is the bit that tends to make that whirling sound when we actually provide power supply to the hard drive itself. All right. H is a cluster, and a cluster is essentially a collection of sectors that make up one data storage or data storage of a particular item. Okay. Now moving on to SSDs, going to play the video there. Let's try and pay attention to it as well. I would like to see a bit more involvement of the forensic investigation science students. I know this is quite a well-known area for some of our cybersecurity students, but I would like to see a bit more participation from our FIS students, please, if possible. Okay. And it's fine to also say the wrong option as well. That's absolutely fine. Great. So that's SSD. We have the basic components that make up an SSD. So we have 5 separate components being highlighted there. Anyone willing to tell us what number 1 is? Thank you, Oliver. So number 1 is the controller. The controller is basically the CPU of the SSD, and it's responsible for understanding all of the data that is stored within the, I don't want to name it, all of the data stored in number 5. And it's also responsible for reading and writing data into number 5. And essentially what it does is that it reads the way that, so what you would have within number 5 is various different cells. And those different cells can either be charged or discharged. So if you have a charged cell, that would essentially represent the 1 bit of a data. If you have a discharged cell, that would essentially mean the 0 bit of the data. So when the controller is reading the information within number 5, it's going to identify which of those data are 1s, which of those data are 0, and process that information and hand it over to the computer. And that's the data that you and I get to view. So that's 1. 2, any idea what number 2 is? Thank you, Naeemullah. So 2 is the DRAM, or the dynamic random access memory. That usually tends to store a little bit of metadata, general information about physical and logical addresses within the actual data stored in number 5. And sometimes it can also keep some files or data that are regularly used by the machine or the user. Okay. It's not every SSD that is going to have that number 2. So just something for us to be aware of. Are you sure about 4 being the SATA connector, Siam? I mean, there's a SATA connector there, but it's not 4. Okay. So the SATA connector is number 3. Yeah. Thank you, Scott. So number 4 is going to be the power connector, which essentially provides power to the SSD. And finally, number 5, our storage units that control and hold all of the data. Do we know what that is called? Thank you, Oliver. So those are the NAND flash memory chips. Okay. And those essentially house all of the different cells that basically represent the data that is stored within that particular device or drive. Okay. So those are generally the 2 forms of storage mediums you would encounter. I know there's new standards of hard disk drives nowadays, new standards of SSDs. We have the NVMe, the non-volatile memory express SSDs, etc. Those usually tend to have more application for things like gaming, etc. But the general core functionality of how these different SSDs behave is essentially the same. The difference usually is mostly speed and the type of connectors that they have between them and the motherboard on your own computer or your own system. All right. But in terms of comparison, what you generally find is hard disk drives are generally considered to be slower than SSDs. And of course, so I have an SSD here with me. You can see it's generally a lot more compact and smaller than a hard disk drive. And SSDs can even be smaller than this. I have a 2 terabyte SSD drive here, an external drive. So you can see SSDs are usually quite smaller, which makes them really compact and ideal for some of those different applications that are not your standard computers. So for example, things like laptops or IoT devices, or some of the more embedded SSDs that we tend to see in mobile devices, etc. So they are more ideal and equipped for those types of things, and are generally considered to be faster. They are not mechanical by nature, so you can see almost everything here is wired and embedded to the actual little motherboard chip that we have within the SSD drive. That makes them a lot more durable because they don't really have too many different mechanical components. Yeah. Is there any advantage to having a hard drive to the SSD? Well, first and foremost, they're cheaper. So hard disk drives generally tend to be cheaper. there's the general argument that SSDs are not, SSDs are more durable than hard disk drives because they don't have all of these different mechanical devices. But I think from a forensic standpoint, I would generally say that hard disk drives are usually much more easier to fix if you have an issue with any of these different components. So if the actuator arm is broken, for example, this can easily be replaced. If you have any issues associated with, say, the spin donor, this also can easily be replaced as well. And even when you look at the actual platters themselves, they are coated with magnetic field, but at the same time, they also have a protective layer protecting the actual surfaces of the platter. So this also protects it from things like dust, general wear, and that sort of thing. Okay, so I would say from a forensic standpoint, this is probably one of your safest bets when it comes to recovering data from a damaged drive or a damaged device. Whereas with SSDs, because of their unique nature of using that flash memory, it makes it quite difficult to recover data. And I know there's now a new approach called chip-off, which generally allows us to be able to remove the actual NAND flash memory that we have there and try and reconstruct the data that we find within them. But again, this is also a very, very complex and tedious process. Okay. Yep, hard disk drives are still good for high capacity, as Scott mentioned there. So what you'd usually find is if you go to a lot of data centers, you'd usually have these array of different hard disk drives, which we call RAIDs. So redundant array for independent disks, and those sort of storage mediums allow us to collate multiple different hard disk drives and store information inside them. So yeah, so for example, here, when we look at the comparison there on the table, you see that for commercial disk storage mediums, hard disk drives would usually have a higher capacity. So now we're only referring to commercial hard disk drives. So hard disk drives that are available for commercial consumption, etc. And they can go as large as up to 20 terabytes, in some cases even more. Whereas commercial SSDs, maybe at best, you probably get 8 or maybe 10 terabytes. But when it comes to enterprise-related storage mediums, so those are storage mediums more dedicated for specialized environments. So, think of things like factories or industries, etc. SSDs usually tend to have higher storage formats, but that also makes them a lot more expensive than hard disk drives. So I think making the decision on which one to buy for personal use, then you can weigh up those based on your requirements and what you plan on utilizing the system for. But from a forensic standpoint, these are generally the two forms of storage mediums you'd always expect to encounter, particularly when you're dealing with computer devices. And also, as I mentioned, when it comes to things like recovery and reconstruction or fixing the actual drive itself in cases where there might be some element of damage, I would typically say that the hard disk drives are usually the safest bet. Okay. And again, yeah, you don't only find them in your standard day-to-day computer devices. So for example, I have this component here with me. So if you look at this, for example, one could easily assume that this is actually a CPU tower or some form of medium or smaller CPU tower, all right? But this is not actually a CPU tower. This is the old version of the Sky decoder, all right? So one of the side activities that I like to do is I like to break and open various types of hardware components to really get a general idea of how they work, how they store data, how they store information. And you can see essentially what this has within it is a standard Seagate hard disk drive. All right. So yeah, these are things that I usually find in various types of devices and artifacts laying around your house. One of the projects that I like to embark with students, particularly when it comes to things like final year project dissertations, is investigating and exploring data from unconventional devices like this one in this instance, because sometimes retrieving the data within these different storage mediums can also be very difficult because we're not really sure on the nature or the type of data that is stored in those different devices. Okay. So what and how can we image? Well, we mentioned earlier that we could utilize storage mediums to actually conduct the imaging process itself. We don't always have to do this through the use of software tools like FTK Imager. We have advanced forensic tools that can actually conduct the action of hardware write blocking for us, but at the same time also allow us to carry out the imaging process on the file. So what you have there on the left-hand side, well, my left-hand side of the image is the actual evidence hard drive. And then on the right-hand side, what you have is the actual the control copy and the working copy that is going to be utilized for the investigation and analysis. And you also have a USB there as well. So that is something that somebody could potentially use to replicate or create an image and add that image into the USB without requiring the need of a software. Yeah. These are quite expensive. Something like this goes for around $1,200, which is generally much cheaper than the TD4. The TD4 is the standard sort of de facto current state-of-the-art hardware write blocker and imaging tool that is used in the market at the moment, which we talked about last week in the lab sessions. Software imaging, we're familiar with FTK Imager, but FTK Imager is not only the tool that allows us to do this, there are other multiple tools that can help us with this. So Tableau is one of them, EnCase, X-Rays Forensics. The DD command in Linux would also allow us to be able to directly copy any form of data to an external source. I would strongly recommend, particularly for not just the cybersecurity students, I think for all of you, especially if you want to go into this line, I would strongly recommend experimenting and playing around with these other software as well, because they do have trial versions that one could utilize and play around with to get a general idea of how they behave and function and some of the different features that they may have compared to FTK Imager. So imaging process, what is the imaging processing like? What we've been doing so far is physical drive imaging. That essentially means that we copy all of the data stored within that particular hard drive, including all of the partitions that make up that hard drive. So if we have a hard drive that has 3, 4, 5 partitions, if we image that hard drive, we're going to get everything contained within that hard drive. Okay. This is quite different to logical drive imaging. With logical drive imaging, we're only interested in one partition. And this has a lot of use cases, particularly in incident response. So there are situations where you would have a shared system where multiple different users make use of that system, and all of those different users have their own different partitions. Or you have a system with dual boots. So you have a system that is running maybe 2, 3 different types of operating systems. And in that particular instance, we're only interested, or the authorization letter that we have, or the warrant, the search warrant that is available to us, only highlights that specific drive as the area of interest for investigation. So in those instances, it would be wrong of us and unethical of us to make a full data acquisition of all of the various different partitions. Rather, we only focus on the single partition that we're interested in. Okay. In terms of forensic formats, the raw format is what the alien image came in. So that's standard raw format. The image comes as it is, data as it is. There's no any form of utilization of any proprietary software to actually convert that particular data into a different format. All right. The main advantages of generating or creating data in the raw format is that, one, we don't associate the data with any metadata, so there's no any form of or element of compression associated to that data, as we will see later on with the other proprietary formats. It's also quite useful because it can ignore minor data errors within the data itself, and most forensic tools should be able to read a raw format without any issue, because these are not proprietary style formats. The disadvantages with this is that no compression can take place. So if we have 1 terabyte of evidence, we need to make sure that the destination also has 1 TB of space for it to be able to replicate that image. So that can raise a lot of complications, particularly when we consider things like storage or data transfer between multiple different stakeholders. There's also the issue of lack of metadata. So we're not able to associate any metadata to it. So for example, if we needed to generate certain information about the case profile, the case details, the people involved in the investigation, we cannot add all of those different additional image to it as well. If we're to do any forms of validation check, that information would also have to be stored completely separate from the actual image itself. Right? Proprietary formats are quite easy to use, mainly because of data compression. So the way that data is stored, that data applies a lossless compression. That lossless compression prevents that data from being tampered, but it's able to store that data in a unique approach or manner that allows the data to be shrunk in size within the actual storage destination. So it makes it very, very easy for us to be able to transfer that proprietary file across different users or different people who are interested in the investigation. Also, the metadata that we can associate with the actual file itself. So things such as the names of the people involved in the investigation. And finally, data encryption, which is a crucial element. It allows us to add that additional layer of security to prevent unauthorized people from having access to that data or that information, which is what we did anyway with the advanced forensic format in the lab session. Yeah. One other advantage as well of proprietary file formats that I forgot to mention is the fact that it allows what we call checks of error checks. So it uses what we call a cyclic redundancy check. And essentially, with the cyclic redundancy check, every block of data contained within that particular device is going to be checked for any data read errors, etc. Okay. Some of the various different tools and the types of images that they provide and create. So it's worth noting this as well. So at least, you know, if you happen to be working in the field one day and you're using one of these tools, these are the only images or formats that you can create your image in. Yep, I did think, yeah, I did mention this. So yeah, it does for every block of data. So for example, for it to have a single evidence file, as we can see here at the top, very top area of this particular image, we have the header, which generally contains case information associated to the case. Then for every data block, we are going to utilize that cyclic redundancy check to make sure that that data block that is being copied across does not really contain any data read errors. Okay. And the same thing is also applied even when we're splitting or segmenting the files into several different files. Yep, covered this already. Yeah, some of the other imaging formats that you may come across are imaging formats like L01. So L01 essentially refer to any logical drive that has already been imaged. So this is quite different in terms of the way the information is stored. So for example, with any logical partition, you won't get the MBR associated to that actual drive itself. So remember when we said for a full physical image, we get everything, including all of the partitions and the master boot record. Master boot record is very, very helpful sometimes because it serves two purposes. One, it gives us general information about the full structure of all of the different partitions, including their file system details and any other metadata associated with them, including when they were created, etc. And secondly, it also contains a little program that communicates directly with the computer to let it know that a drive is available and it can utilize that drive to store data or retrieve data from it. So yeah, with logical partitions, we do not get access to the actual MBR, but we get access to a preamble that is associated to that partition. That preamble is what is going to contain the general properties of that particular image. So yeah, just something for us to be generally aware of. Good. Yeah. So other types of evidence files, the SMART format is there, the advanced forensic format is there. To be fair, most of these proprietary formats are very, very much similar to the expert witness format, the E01. The main advantages really is based on the type of tool that is being utilized by that person to actually investigate and analyze the image, and the other additional elements that they add, such as the encryption or security layer that they add to the image itself, and things like data segmentation and that sort of thing. Yeah. Yep. I think, yeah, we mentioned this earlier. So yeah, we can create logical images, and those will come in the format of L01, something for us to just take note of. How long does it take to create an image? It's quite easy to get a general idea. One of the things that we tend to refer to is the MSTR. The MSTR is the maximum sustained transfer rate, and this is something that you usually find within the package or description information associated to that particular hard drive. So we look at the storage capacity and we divide that storage capacity by the MSTR. And that's very, very useful for us because it gives us general information about how long it will take us to actually create that imaging process in case we need to engage in other activities while the imaging is being conducted. Yeah. But data doesn't only reside in these different storage mediums that we've discussed. So data is not only located in these different devices or storage mediums. Data can also reside in RAM, as we mentioned earlier, the random access memory. Data can also reside in network. So yeah, one of the things that we tend to do with the third year digital forensics module is start to focus more around network forensics, utilizing tools like Wireshark to really try and extract as much network data as possible and start focusing more heavily in things like incident response and that sort of thing. Okay. Machine critical computer systems. So these are machines that are critical to any form of business functionality. These types of machines are very, very critical, and we always have to put that into context when we're thinking of data acquisition. Okay, because even that data acquisition procedure could pretty much impact the actual utilization of those different systems. So it's something that we need to be aware of. And in those instances, perhaps it might also just be wise to utilize a backup of those different files and access those backups for your investigation and analysis. Yeah. Great. So what have we really discussed? Well, we've looked at different formats of creating data image. We've discussed hardware imaging. We've looked at or discussed multiple different tools that we can use for software imaging. We're quite familiar with FTK imaging. We've already played around with that a little bit. We've discussed the different types of technologies associated with storage mediums and the implications that could have for digital forensics. I wish we had a bit more advanced tools within the university itself so we could do things like data reconstruction that is available on these various different storage mediums. But that is a very, very complex process and requires very, very specialized tools. And I don't think that is something that is going to be made available to us at any point in the foreseeable future, as things stand with most institutions currently. Okay. Now, we've also talked about imaging formats. We've looked at or discussed the various formats that we can create data imaging, one of them being the raw format, the other being the proprietary formats, such as expert witness format, the E01, or the advanced forensic format, or the smart format. For the coursework, as I mentioned, that decision is completely up to you. I just have to see some justification. And that is also an opportunity where some form of utilization of secondary resources and referencing some of those secondary resources could come into play when it comes to justification. And when you're justifying or utilizing those secondary sources, don't just provide a secondary source from some, online paper. Utilize things like academic journals, academic papers, or reports that are being generated or made available by organizations that are heavily involved in this area, such as NIST and the likes of those. Okay. Good. Now that brings us to the end of the talk itself. This week in the lab sessions, what I really want us to start looking into is begin our investigations with FTK Imager. I know in the past we've been mostly focused on data acquisition, etc. But this week I really want us to start doing some investigations. So tomorrow I have a set of labs that I want you guys to engage with. That would, I think I'm getting some feedback noise. Yeah, so tomorrow I have a set of labs that I want us to engage with that would really help us explore evidence files and collect information from those different files and do more in-depth investigation, particularly when it comes to things like signature analysis and examining various types of data signatures. Okay. Any questions at this point before we end the session? Okay. That looks like a no to me. In that case, I suppose we could end the session here. Thank you all for your time and hope to see you all tomorrow. Oh yes, I would spend a bit of time to give a bit more guidance on the coursework by tomorrow. This week is the week that we're going to start releasing the actual evidence images. So I believe from the lab on Thursday, you should be able to approach the evidence custodian, which is Forward in this case, and actually ask him for the evidence item so you can start utilizing it or creating the image from the evidence item itself. Okay, so I'll give a bit more general guidance about it tomorrow, and from Thursday, those evidence items should be available for you so you can begin the coursework. Yeah. No problem. No worries. Thank you all. Thank you for your time. Thank you. Bye.